We now wish to look at a topic called SVM, which is support vector machines. So this is basically application of linear algebra in the field of pattern recognition and machine learning. Specifically, it is a supervised learning scheme, learning mechanism. And when you say supervise, the supervision comes from data for training. So let's set the context of this problem or the context of this technique to being used. So let's look at data of two classes. The question is, given data of two classes, can I find a linear hyperplane that separates data into two distinct classes, class 1 and class 2. Okay. We may not be able to do many cases uniquely. So you may have multiple solutions or no solutions. The question is, which is best and why? What type? Linear, meaning you are basically trying to pass a hyperplane in some dense set of data, and you want to find which is the best, why, when, and all that. Okay. Just look, there are some interesting problems where you may never be able to do it. So let's take this problem where we have data like this. Now separate all x from 0. You can do one separation like this, but these x's remain. You can do a second separation like this, but these x's remain. Therefore, there is no single linearly separable plane which you call a classifier that separates all zeros from x's. Very simple problem. So how do we go about doing this? Because we have to do it in very large dimension and we have to do it very frequently. Not coming. Oh, okay. So the idea of support vector machine is basically given two classes data, two classes of data, I want to find a linearly separating hyperplane, this may be affine 2, okay, such that the gap between these two, this gap is maximum. The reason is, while implementing, after all you have to implement with real numbers, instead of this you may end up implementing more like this or like this. So to make sure it is robust and reliable during implementation, it's always good to give gaps. So it's basically looking for tolerance and other things in other contexts of circuits. So how do I find this? Okay. You have multiple solutions, all these do the job. Okay. The idea of support vector is as follows. You have data of class 1, let us say, data of class 2. Find the points here. Find the point closest to the boundary here. Suppose this distance is d. The maximum distance between the closest 2 points belonging to class 1 and class 2. The support vector is one which goes like this, whose distance is, let us say, d by 2 on both sides. This is the idea of support vector. Support vectors means those data points, vectors in class 1 and class 1 and class 2, which define the boundaries here and finding the gap between them and getting the center point, so that this classifier will support a maximum distance between the two classes. Okay. A more technical name for SVM is training linear machines with margins. Training linear machines with margins. Let us look at one interesting case. Suppose the data is not linearly separable. What do we do? What motivation we have? We have motivation from PCA. PCA looks at given data in Rn, look for representation of the data in Rk where k is much less than n. So basically PCA looks at efficient lower dimensional representation. We saw that with the satellite data. From very large number, from 240 odd number, it was reduced to about 15 or 18 or 25. So almost 90% reduction, and still very efficient. 90% reduction of data with more than 99% accuracy. Okay. SVM does something interesting. Suppose you have a dimension Rn, you look at Rp where P is greater than n. Sometimes P is much greater than n. Therefore, the idea about support vector machine is you have data in a given dimension. Suppose it is not linearly separable, which is quite frequent, not linearly separable, then look for a higher dimension, that is your project. In PCA you are projecting it into lower dimension, here you project it into higher dimension. It's almost the analogy of saying I am searching for a house in the city, I am going from road to road. The best way to search the house is to fly like an eagle, go to higher dimension and look down where you can easily spot. This is really what it is. So in higher dimension, possible to use a linear hyperplane to separate classes, separate data into two classes. Okay. How to understand? Look at a problem. Consider two class data. Class 1 is data 0.5, minus 0.5, 1, minus 1. You represent this as symbol X. Class 2, you have data 2, minus 2, 3, minus 3, 4, minus 4. Represent this as 0. So if I really look at this, this is a one dimension data. I have origin 0. C1 is X. So these are numbers 0, 0.5, 1.0, 2, 3, 4, 5. This is minus 0.5, minus 1, minus 2, minus 3, minus 4, minus 5. This is X. What is X? 0.5 is X. Minus 0.5 is X. 1 is X. Minus 1 is X. Class 2, 2, 3, 4, minus 2, minus 3, minus 4. So I have data like this and I want a linear separator. We saw very similar to non-numerical data in the previous explanation, but you can't find a linear separator anywhere which separates X from 0. This is where SVM helps, SVM does. What SVM does is interesting. This is in dimension 1, this is in R1. Now look at a mapping f of x which takes R to R2 as given xi belonging to R, map it to xi comma xi squared belonging to R2. So you have increased the dimension by 1. Now how does the data now look like? C1 now looks like 0.5, square of 0.5 is 0.25. This is one data. Minus 0.5, square of that is plus 0.25. This is another data. 1, 1, minus 1, square of minus 1 is plus 1. This is now the upward higher dimension projected class 1. Similarly, what about the class 2 now? 2, 4, comma, minus 2, 4 again, 3, 9, minus 3, 9, 4, 16, minus 4, 16. These are the data sets. Now again do a representation. Now this is in R2, 0, 0.0, 0.5, 1.0, 2.0, 3.0, 4.0, 5.0, etc., etc., minus 0.5, minus 1.0, minus 2, minus 3, minus 4, minus 5, minus 6. Here 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 all the way. So I now represent the points. How do the points look like now? The points are 0.5, 0.25, 0.5, 0.25, minus 0.5, 0.25, then 1, 1, 1, 1, minus 1, 1, minus 1, 1. So 4 points here. Then 2, 4, minus 2, 4, 3, 9, minus 3, 9, 4, 16, minus 4, 16. Now this is how the thing looks like now. Now it's very interesting. I want to separate all this red from blue, and so it's very easy for me to pass a line here. In fact, any of the lines here will do the job, and the support vector machine, a function of the type z of x1, x2, which is the second point here, of the type 0, x1 parallel to y axis plus x2 minus 2.5 equal to 0. This will do the job. Simple, linearly separable with a margin of 1.5. Basically it separates 1 from 4 with a margin of 3 on both sides. So half a margin of that is 1.51. So this is how SVMs work. This idea of shifting from a lower dimension to higher dimension representation of data, where here linearly separable can happen. This is called kernel methods. Kernel methods or sometimes kernel tricks. This is a niche area, meaning it's not very general, but it has solved very interesting problems. So there are even books on kernel methods. There are half a dozen books exclusively on kernel methods. The choice of the kernel function, this is not only critical but also strategic. This needs experience too. And this SVM is also related to regression models, which we will deal later. So what it means is, if you take a much broader and more generic view of things, or a upward or a more mature look at the situation, you may be able to solve problems in our dimension. That's exactly why you go to experienced people. Experienced people can see where you are knotted and see it from a larger perspective, from a higher angle, and solve those. That is socially, but here this is mathematically. Okay, thank you.